Welcome to Electronic Pariksha channel. Today we'll discuss the problems related to diode circuits of analog electronics. Okay. Total we are going to discuss 15 problems today. So these are the problems. These are the previous year problems of GATE, IES, NILT, ISRO, Mizoram PSU, and RRBSSC. There are many more problems like this, which are previous year problems and very important problems. Okay. Today in this class we'll discuss all these important problems. First, coming to the first question, in the circuit shown below, the switch was connected to position 1 at t less than 0. Okay, this is switch is connected to position 1 at t less than 0. At t is equals to 0, it is changed to position 2. Assume that the diode has 0 voltage drop and a storage time Ts. There is a storage time Ts. For t varies from 0 to Ts, what is the VR? See, we have already seen Ts is a storage time that is taken by the diode to switch from forward state to reverse state, forward conducting state to reverse conducting state, conducting state to, reverse blocking state. So when the voltage across the diode is flipped, changes from positive side to negative side, it takes some time, that is Ts, storage time, which is required for the diode to understand that the voltage across the diode is reverse biased, and it is the time taken by the diode to switch from forward conducting state to reverse blocking state. Actually, this is the TRR. We have to say this is TRR, reverse recovery time, whereas this reverse recovery time includes TS plus TR. This is the storage time. This is the transition time. Okay, graph will be like this. This is the forward current that is flowing. This is the forward current that is flowing. When the voltage across the diode is flipped, means changes to reverse bias, the same current flows. The same current flows, but in the reverse direction. Means same current flows. As the voltage is reversed, we have to consider the current is going in a reverse direction. And this is a storage time. This is Ts, storage time. After storage time, it will gradually reduce and come back to 0. Okay, this is a transition time, TR. This is a storage time and this is a transition time. All put together is a diode reverse recovery time. This is the time taken by the diode to flip from forward conduction state to reverse blocking state. Okay, now coming back to the question. So initially the diode is conducting. Okay, initially the diode is conducting in this way. And what is the current flowing through it? We can calculate the current flowing through the diode as so here the diode is in the forward position. So the voltage across output voltage will be approximately 5 volts. The entire voltage drops across this load resistance. Okay, across this load resistance. Load resistance is 1 kilo ohm. So current will be approximately 5 milliamps. Okay, so current will be approximately 5 milliamps, and voltage at the output is 5 volt. So when it is switched to position 2 like this, when it is switched to position 2, the diode becomes reverse biased. Immediately the diode becomes reverse biased, but the current through the diode cannot change to 0 immediately. So the current remains the same. Same 5 milliamps will be flowing for Ts time period. For Ts time period, that is a storage time. So during this time, what is the output voltage? The output voltage will be equal to minus 5 volts. Why minus 5 volts? Because here, when the transition happens, the diode acts like a closed circuit. Here, the diode acts like a closed switch. Okay, this is the load resistance RL, and this is minus 5 volts. So, what is the voltage across RL? It will be nothing but, if you apply KVL here, it will be nothing but the minus 5 volt only, because both are parallel. Exact minus 5 volt will come here. So output is equals to minus 5 volt. Answer is option A. We'll see the next question. This is asked in Odisha Public Service Commission and GATE 2012 also. The IV characteristics of the diode in the circuit is like this. So current is V minus 0.7 divided by 500 amperes when input voltage is greater than 0.7. When input voltage is less than 0.7, it is 0 amps. So here, by applying Kirchhoff voltage law in the circuit by KVL, we get the equation V is equals to 10 minus 1 kilo ohm is a resistor, so 1000 I. Whereas I is equals to, he has given in the equation, if V is greater than 0.7. So in the equation it is given as, we have to substitute the I value, that is V minus 0.7 divided by 500 amperes. If you solve this equation, V is equals to 10 minus 2 V minus 0.7, that is 3V is equals to 11.4. So V is equals to 3.8 volts. Okay. Now you calculate the I value. Now I is given as V minus 0.7 divided by 500. The question itself it is given. So V is 3.8 volts. Substitute here 3.8 minus 0.7 divided by 500. You get I is equals to 6.2 milliamps. So the answer is option D. We'll see the next question. Here, we'll see the next question. In the following circuit, the limiter circuit, the input voltage V1 is 10 sine 100 pi t applied. Assume that the diode drop is 0.7 volts. Here, this silicon diode is still. Diode drop is 0.7. This and this. This is the Zener diode. Okay. This is the 1 kilo ohm resistor. And this is the diode D1, normal silicon diode D1, whose drop is 0.7. This is the Zener diode, 6.8 volt. And this is diode D2. Here is the output voltage. This is V1. So what is the maximum and minimum output values he is asking? So what happens here? V1 is a sinusoidal wave of 10 volts amplitude. This is 10 volts and this is minus 10 volts. So during the positive half cycle, what happens? Diode D1 conducts and current flows in this way. Okay, because diode D2 is off. So the output voltage will be here 0.7 voltage drop will be there, and here 6.8. The output voltage will be 7 volts. So during the positive half cycle of the input, D1 is on, D2 is off. So the output voltage will be VD1 plus VZ1, Zener voltage as well as diode voltage. That is 0.7 plus 6.8, that is 7.5 volts. So during the negative half cycle, what happens? During the negative half cycle, that is minus and plus. D1 is off and D2 is on. Current flows in this direction. During the negative half cycle, D1 is off. So no current flows through Zener. D2 is on. So output voltage is minus 0.7. Because the voltage appears like this, plus minus 0.7. So the answer is option C. These are the maximum and minimum values. We'll see the next question. Which is the correct waveform across the capacitor of the filters of the following circuit? Okay, this is the center tap full wave rectifier. Center tap full wave rectifier, whose output will be like this. Center tap full wave rectifier output is like this. Only positive half cycles, pulsating DC. When it is fed to the capacitor, it will appear like this. So capacitor charges and discharges, charges and discharges, charges and discharges. Okay, so the output is, see here, 3 cycles, 1, 2, 3. 3 half cycles are there, so 3 ripples will be there. So here we have to consider the answer as option D. This is the answer. This cannot be the answer because this is for half wave rectifier. Half wave rectifier with capacitor filter, not for full wave rectifier. This one. This is for full wave rectifier. We'll see the next question. Like the video, share the video, and subscribe to the channel for better content and more videos. In the half wave rectifier, if Vi to the diode is 20, Vin is 20 sine omega t. What is VDC? VDC is equals to Vm by pi. We know the formula. Vm is 20 divided by pi is equals to 6.37 volts. So the answer is option A. Next question. The main advantage of the bridge rectifier over the full wave rectifier with center tap. That is less ripple. No, both are same. Both are full wave rectifiers only. So the ripple factor for full wave rectifier, either it can be bridge or center tap, it is equals to 0.482. So it is same. No transformer needed. No, both require transformers. Both require transformers. Only thing is bridge requires normal transformer, center tap requires center tapped transformer. Third thing is peak inverse voltage of each diode is off. Yes, for center tap, peak inverse voltage is 2 Vm, 2 times of Vm. Whereas for bridge, it is Vm. This is correct. Peak inverse voltage is double. No, it will be halved. So the main advantage of the bridge rectifier is the peak inverse voltage of the diode is half. This is the answer. Next, precision diodes can be used as half wave rectifier, full wave rectifier, and clipper and clamper. All of them. Precision rectifiers can be used in all the circuits. Precision diodes, so it can be used in all the circuits. The disadvantage of the half wave rectifier is that. So, what is the disadvantage of half wave rectifier? Ripple content is very high. The ripple factor, if you see, ripple factor is 1.21. This is very, very high. Ripple means ripples are very high. So we'll see the options. Diode must have high peak inverse voltage. No, this is for center tap. Diode must have high power rating. No. Output voltage is difficult to filter. Yes, means he is telling that there are high ripples. There are higher ripples in the output. That's why it is difficult to filter in output. Diode must have high current rating. No. Answer is option C. Transformer utilization factor of a half wave rectifier is 0.287. This is very important. We'll see the comparison table. Half wave rectifier, center tap, full wave rectifier, and bridge rectifier. Okay. First thing, if you see the ripple factor for half wave rectifier is 1.21. Center tap is 0.482. Bridge is also 0.482. Second thing, transformer utilization factor. Okay, this is T. Transformer utilization factor is for the half wave rectifier it is 0.287. These values are very important. It will be asked in examination. Many examinations have asked these values. For center tap it is 0.693. For bridge rectifier it is 0.812. So these values you must memorize. Third thing is ripple frequency. Ripple frequency. The ripple frequency is same as input frequency for half wave rectifier. For center tap full wave rectifier, it is 2 times of input frequency. For bridge rectifier also, it is 2 times of input frequency. This is the basic comparison. Next, the DC voltage of a half wave rectifier is. The DC voltage of a half wave rectifier is Im by pi. Even this we'll see the DC voltage. Okay, this is a half wave rectifier. We'll see the comparison here itself. Otherwise, we'll carry down this comparison. Same comparison will continue. Fourth one, DC voltage. That is output average voltage, VAVC. For half wave rectifier it is Vm by pi. For full wave rectifier it is 2 Vm by pi. 2 Vm by pi. Okay, this can also be written as Vm can also be written as IDC. Okay, Vm can also be written as Im into RL. Can also be written as Im RL by pi. 2 Im RL by pi. 2 Im RL by pi. Okay, next comes RMS value. This is Im by 2. This is Im by root 2. For full wave rectifiers, it is Im by root 2. For half wave rectifier, it is Im by 2. So from this, we can tell the answer is Im RL by pi. The answer is option B. So, and we'll see the next question. If one of the diode in a full wave bridge rectifier opens, the output is. We have seen this kind of problem in the previous lecture also. In the bridge rectifier, This is the primary and this is secondary. If anyone, there are four diodes. Simultaneously, what happens? For the positive half cycle, two diodes conduct. For the negative half cycle, another two diodes conduct. This is the principle of bridge rectifier. If any one of the diode fails, see here, during the positive half cycle, for positive half cycle, here if you give the notation is D1, D2, D3, D4. Positive half cycle is G2 and D3 conduct. For negative half cycle, D1 and D4 conduct. If any one of the diode fails, only half of the cycle will come. Output will have only half of the cycle. Either it can be positive or only negative half cycles. So it acts like a half wave rectifier. Answer is option C. Ripple factor of an ideal rectifier is 0. What is the ripple factor formula? The ripple factor is given as IRMS divided by IDC whole square minus 1, or we can also tell this as VRMS divided by VDC whole square minus 1, or RMS value of the ripple voltage, output ripple voltage divided by VDC. These are the three formulas. So this is very important. RMS value of the ripple voltage divided by VDC. Okay. So basically we need the ripple voltage should be 0. There should not be any ripples. So ideally speaking, we should have the ripple factor is equals to 0. We don't want the ripples to exist in the output. So ideally the ripple voltage should be 0. So answer is 0. Next, the RMS value of the half wave rectifier current is 50 amperes. Okay, its RMS value for full wave rectification would be, yeah. See this question, we'll see the RMS value of a half wave rectifier is Im by 2. So for half wave rectifier, if you substitute here, it is 50 is equals to Im by 2, which gives Im is equals to maximum current is equals to 100 amperes. Now RMS value for a full wave rectifier is Im by root 2. So 100 divided by root 2, which is equals to 70.7 amperes. So answer is option D. Next question. If the PIV rating of the diode is exceeded, what happens? PIV is the maximum reverse voltage. So maximum reverse voltage a diode can withstand. A diode can withstand. If the reverse voltage increases, goes beyond PIV, the diode gets damaged. So answer is option B. Diode gets destroyed. So our next question, an AC supply of 230 volts is applied to a half wave rectifier through a transformer having a primary to secondary turn ratio of 12:1. The peak inverse voltage is. So here we'll see this question. This is the primary winding and secondary winding. This is the diode and resistor. This is the voltage V2. This is V1. And this is N1 turns and this is N2 turns. So first, he's telling the turn ratio is 12:1. First, we have to calculate the V2 voltage. Okay, V2 by N2, V2 by V1. The ratio of secondary voltage to primary voltage is equal to secondary winding to is equal to the ratio of secondary winding to primary winding. That can be equated like this: V1 is 230 volts. N2 by N1 is 1 by 12. So V2 is equals to 19.167 volts. So what he is asking here, the peak inverse voltage is, peak inverse voltage for the half wave rectifier is equal to Vm. That is the voltage appearing across the secondary. That is equals to V2 again. So PIV is same 19.167 0.67 volts. That is option is answer C. Sorry. Actually, here what happens is the peak inverse voltage is the maximum voltage that we have to take. So here V maximum is nothing but the voltage across the secondary winding multiplied by root 2, because this is the RMS value. 230 volts is the RMS value, so we got the RMS value. So multiplied by root 2. So here 19.67 multiplied by root 2, which is equals to 27.11 volts. So the answer is option B. We'll see the next question. Which rectifier requires 4 diodes? It is bridge rectifier. Bridge rectifier requires 4 diodes. Requires 4 diodes. Okay, so the answer is option full wave bridge rectifier. Option A. So here half wave voltage doubler requires 2 diodes, 2 capacitors. Voltage quadrupler and a full wave voltage doubler requires 2 diodes, 2 capacitors. This is very important. Okay. Now we'll see next question. Like the video, share the video, and subscribe to the channel for better content and more videos. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.